So, okay, welcome to this talk. So this is a talk in a mini talk series on modular flavor symmetries, which is in principle part of a bigger event, which is hopefully yet to come. Today, it's our great pleasure to have Saúl Ramos-Sánchez giving a talk. Saúl got his PhD under the supervision of Bethe in Bonn some time back. Then he was a DESY fellow, and after that he moved to UNAM, where he has a professor position at the moment. So we will talk about the top-down, we'll give an overview talk on the top-down approach in this business of modular flavor symmetries. So, and the title of the talk will be Modular and Eclectic Flavor Symmetries from String Compactifications. Please go ahead.
Well, thank you very much. Thank you very much to other organizers for giving me this opportunity to talk about this interesting topic here today with you. It's very nice to see very friendly names, known names in the list of participants. So I'm very glad to be with you. So let me just come to the point. I will just start by giving you a very brief summary of what we heard yesterday by Guillaume in his talk about modular symmetries and how they are related to these finite groups and finite modular symmetries that we might use as family or flavor symmetries as well. And then I will jump to orbifold compactifications, and I will explain what the properties of the flavor symmetries that appear there are, particularly that they are traditional modular flavor symmetries together, and that they build something called the eclectic flavor scheme or eclectic flavor symmetries and local flavor unification. And then I will continue to give a very brief summary of what people have done on magnetized toric when they look at the deep brain compactifications and toric together. So let me just start at the beginning. So modular symmetries arise from a toroidal compactification. So you start with a two-dimensional torus like this done here, that you can also describe by these two vectors. You set one of these directions to be the vector, the unitary vector 1, and then the second vector to be the so-called complex structure modulus tau. And this complex structure modulus will be a complete description of the geometry of the two-dimensional torus. What is interesting is that not only tau will describe this torus, there will be a series of different taus, let's say tau and tau prime, that are related by SL2Z transformations that describe exactly the same torus. That is, if you take an element of SL2C and transform a complex structure tau, by this kind of transformation, you will arrive to a given tau prime, and this will give you exactly the same construction. And then you say then that SL2C is a symmetry of a torus. SL2C can be defined by these two generators S and T that have to fulfill a series of relations that are written here. And they can be represented by these 2 times 2 matrices that are given here. They are typically represented like this. There are some other representations, but mostly we like this. And in these terms, all the elements of SL2C can be written as 2 times 2 matrices filled with integers and determinant 1. As I was saying, tau lives actually in the complex plane. So let me put it here. This is the complex plane, half of the complex plane, the positive half of the complex plane. But one can show that by using SL2C transformations, you can start in this gray area and arrive to any other point, and therefore you say that this gray area in this diagram is the fundamental domain of modular space. Furthermore, what is interesting as well about SL2C and modular transformations in general and modular groups in general is that you can have something called modular forms. Modular forms are functions that depend on the modulus, in this case the complex structure tau, and that are holomorphic everywhere, including the cusps. They have 2 characteristic quantities, the modular weight n and the level n, so that they transform under modular transformations according to this prescription. So if Yn is a modular form of modular weight small n, then it transforms with the so-called automorphic factor where the modular weight enters here, telling us something about the nonlinearity of the transformation of the modular transformation acting on modular forms. And also there will appear a representation rho of the transformation gamma that I apply on the modular form. This representation is a unitary matrix that belongs to a finite modular group. And this is where flavor symmetries enter into the game according to the prescription that Raúl presented a couple of years ago. So he told us that those finite modular groups that are well known, that are listed here, for example, can be finite flavor symmetries as well. So you can see here that these finite modular groups are nothing else but quotients of PSL2C or SL2C divided by concurrent subgroups of those modular groups. But what is very interesting is that depending on the choice that you take for your finite modular group, either if it is gamma subindex n or gamma prime subindex n, you can have different modular weights. You can realize, first of all, that gamma n tilde prime, is the double covering of gamma n because it comes from PSL2Z and SL2Z. In these two cases, they come from these two different groups. And attached to that, you can see that this gamma n group is related to modular weights that are just even numbers, whereas gamma prime n groups are related to all possible integers. So you have to be very careful about which finite modular group you choose in order to choose also wisely what your modular weights are. So very good. Now, let's come, that was the summary, the short summary that I wanted to present about what we learned yesterday. Now I want to come to our topic today. So we want to start with string theory. String theory, in the best known cases, is a 10-dimensional theory where 6 dimensions are just extra dimensions that we don't observe. And since we don't observe them, we have to compactify them. So usually what you say is that you start with 10-dimensional Minkowski space-time, and then you reduce it to a 3 + 1 dimensional Minkowski space-time that we observe, where we are living, times a compact space that we will call X6 in this talk. So this X6 can be, I don't know, Clavillaw or many other spaces that are possible depending on the theory that you want to start with, the string theory that you want to start it with. But this has to be compact and very small to escape all kind of observations. In this talk, let me just focus on one particular set of X6 that are called factorizable toroidal abelian orbitals. So these are my favorite X6 compact spaces because they are simple, flat, almost everywhere except for a series of singularities or fixed points that I will describe in the following. So let me just say that you have this kind of torus T6, and then you divide a ZN symmetry. Let me further say that it's factorizable and that I can split it in two-dimensional orbitals. So I have this T2 over Zn1, Zn2, and Zn3 for all the 6 dimensions that I want to compactify. Let me take now an example. Let me take, for example, N1 = 3 and divide T2 by Z3. And then I have to choose wisely my torus in order to be compatible with the point group that I want to divide, to be compatible with a Z3. Z3 is just simply a rotation by 120 degrees. Therefore, I just separate my basis vectors of the torus by 120 degrees. So I choose 1 to be 1, and the complex structure that I now will call U instead of tau, just for convenience in string theory, I will call U, the complex structure to be precisely e to the 2 pi I over 3, that is a separation of 120 degrees. So this will be the analogous of tau that I presented before, the complex structure, and I will fix it geometrically in order, as I said, in order to be compatible with the choice of the point group that I was using to divide to get the orbital that I want to construct. The complex structure that is written here can be written also in terms of the metric of this particular space, like this. You can see that the imaginary part of the complex structure is the area or volume of this particular torus divided by one of the components of the metric capital G. We don't care too much about this, but we'll see that there is another modulus, and that's the reason why I had to write it here. So now Z3, this point group that I want to divide, I said is just simply a 120-degree rotation that is given here that you can write also as a 2x2 matrix. And then all the points in the orbifold, once I compactify, are related, these points Y in this complex plane, if you want, or in this two-dimensional real space that is here, that I denote the coordinates to be Y. You can relate all the points in the orbifold by this relation that is here. So this relation tells us that Y is identical to Y rotated plus a shift, a translation that I performed here along the directions E1 or E2, I don't know, in some directions in the stories particularly. So E is what we call the 2x2 matrix related to the geometrical field line of this geometrical space, and N is what we will call the winding number. So this is a two-dimensional integer vector. You can write this kind of vector that you have on the right, just like saying that there is a space group with elements given by these two components, a rotation and a translation, acting on Y. So this element acting on Y give us what is on the right, and the relation given by the orbifold is just simply that Y is related to the action of any space group on Y itself as well. So that is what we have. What is what we have as well? This is the definition of the orbifold. Pictorially, when we just perform the orbifold, what we do is just simply to move out this space group, these space group elements that I just depicted down there. But what happens as well is that there appear certain fixed points. For example, the origin is basically, it's clearly that it's fixed under the rotation. And under the translations as well, because the translations are just complete translations along the directions of the torus in this particular case. But it will happen that these other points that are here in blue are also fixed points. What happens when you do that as well is that many points that are here that are not in blue are related to the points in blue, the points that are inside. Let me just put it like this. Inside this red region, all these points are related to the blue points, and therefore we will say that the blue points depict actually the fundamental domain of the orbifold. So we have this. What happens as well when we compactify in the orbifolds is that these directions that I have here, this one is mapped to this one, and this one is mapped to this one, so that they are actually kept together or clipped together by the action of the space group elements of this orbifold. So at the end of the day, after you put everything together, the original torus deforms to build this triangular pillar. This triangular pillar that is actually depicted as a triangle with equilateral, with equal length sides. This is important because basically here you can see that in principle, you don't see any difference between the sides, and you don't see any difference also among the corners. So there is already at this level a geometrical symmetry that you can see directly here. So let me just go on and now put in this particular context strings. So you can have in this orbifolds different kinds of strings. You have these box strings, these ring strings that are just free to move everywhere in space, in the compact space, and also in our space-time. And you have also these winded strings that are here in brown, yellow, orange, I don't know what. These strings that are in the top that are just winded around the torus once or twice or n times in general. And when you compactify on the orbifold, of course, you are going to see that this string is really winded around, I don't know, a particular direction in this particular compactification. But on top of that, you have very special strings that are the so-called twisted strings that are living together here attached to the singular disk. Here I depicted it with the color red. I have this particular string, and this particular string in the orbifold looks like this. It is attached to the singularity, it's here, whereas the other strings are just simply, I don't know, somewhere, everywhere if you wish. This particular red string is living just attached to the singularity. It turns out that if you don't add fluxes or Wilson lines or anything funny to your particular orbifold compactification, these red strings will appear in all singularities that you have at hand. In particular, you will have 3 copies of these red strings, one attached to each singularity. Since these strings actually correspond to matter states, to 4-dimensional matter states with certain quantum numbers related to their localization in the compact dimensions, you will see from your point of view of 4 dimensions, you will see that there are 3 identical strings, 3 identical states, 3 identical particles that somehow are related to each other, but they are not completely equal, that they perhaps transform among them following certain relations. What else do you have from string theory? You have as well an additional modulus. I told you that the complex structural modulus, that is the one that Guy was telling us about yesterday, the complex structure is fixed in this particular scenario, but there is an additional modulus, the so-called Kähler modulus T, that is built out of the volume of the 2-dimensional cherries and the so-called antisymmetric B field. This is in 2 dimensions. The only component is non-trivial for the B field, and that is all. It defines the complex Kähler modulus T that you have here, and it is completely free. Therefore, what you have here is that all the freedom that Guy was telling us yesterday about is actually now encoded in this particular modulus T. That is, in particular, you're going to find out that there are SL2Z T transformations that you can perform, that you can relate your orbifold to any other orbifold just simply by transforming this modulus T in here. What else? Well, that was an example, right? The T2 over Z3. You can have another example, T2 over Z2, for example, here, where you have the first vector, this horizontal vector set to 1, and the complex structure set to whatever you wish. Here, the vertical vector U, that we will call U in this particular case, can be set to any complex value. It doesn't matter. It will be here or perpendicular to the 1 or in any other position. And it can have also any length it wishes, so it doesn't matter. And in any case, in this particular choice of U, you can as well perform a T2 over Z2 orbifold. It doesn't matter. What happens here is that instead of 3 fixed points, there are 4 fixed points. What happens as well is that the fundamental domain of the torus, the whole square, is reduced to this yellow parallelogram that we have here. And it happens as well that all the things that are related by these arrows, this with this is related, this with this is related, and this is related as well with this other part. So what happens at the end of the day is that this torus that you had in the very beginning, the donut, reduces to this particular T2 over Z2 orbifold that looks actually like a pillow, the foam pillow with 4 corners. This is also invariant under an additional symmetry, the so-called mirror transformation. You can relate the 2 moduli that are here. I mean, the complex structure is free. The Kähler modulus is free as well. And you can relate them. You can simply apply this additional modular transformation that relates these 2 moduli without changing, without altering the orbifold. You can also, if you wish, or if you have a very fancy stabilization mechanism or moduli stabilization mechanism, you could set the complex structure to be I or to be e to the pi I over 3. If you wished, or if you had this fancy stabilization mechanism. If you had that mechanism, only the Kähler modulus will remain free, will stay free, and will build the SL2ZT transformation that we were talking about before. But the orbifold will take particular shapes. If you set U equals I, you will get this raviolo shape. And if you set U equals to pi I over 3, you will get this tetrahedron shape that you have here. So you can have these different forms. And these are actually geometrical forms that people, from the point of view of bottom-up constructions, have used actually to arrive at different constructions with flavor symmetries as well. Let me tell you now about the traditional flavor symmetries that you can have here. This was the very first conception that in 2006 or 2007 was conceived by some fellows in the audience, particularly Kobayashi, Niles, and Ratz were there, as well as Rabi and Pluka, but they are not here. And in any case, what happened back then is that they observed that in this particular scenario, say T2 over Z3, you have 3 fixed points, and from the point of view of 4 dimensions, you have actually a permutation symmetry, an S3 symmetries in particular here. On top of it, they observed that string theory tells us when the particular twisted strings that are living in the fixed points at the fixed points can interact, and when they cannot. When they can, they received they go from the string selection rules, and when not, then they tell you that you cannot write a particular coupling in your theory. So this can be encoded in certain symmetries. In particular, in the T2 over Z3 orbifold, you can encode these selection rules in so-called Z3 times Z3 string selection rules. The first Z3 corresponds to the ability of 3, 6, 9, 12 twisted strings to couple together, and the second Z3 refers to the possibility that only 3, 6, 9 strings can be combined together, but only if they are located at the same fixed point or at all 3 fixed points simultaneously. So very good. These are you can assign charges for each of the strings that you have there in order to fulfill these selection rules, and you can assign also certain S3 representations in order to fulfill the selection rule associated to the permutation group. And at the end of the day, what you have to do is to combine all the symmetries that they figured out in this particular scenario by doing the multiplicative closure. So you perform the multiplicative closure and you obtain this particular group S3 semi-direct Z3 times Z3 from the selection rules, and that what you obtain is the traditional flavor symmetry delta 54. Why do I call it traditional flavor symmetry? Just because it doesn't affect the moduli, and it relates in particular the strings that are, I was saying, living here. For example, I relate these strings, and since I relate them by these permutations and these selection rules, then I will call this a flavor symmetry that is actually traditional because it doesn't transform the modules. I used also the gap ID annotation that is written here, just because it allows me to write many more groups than those that are written with very nice names. So this is a group that has order 54. It has 54 elements, and this is the 8th of these groups with 54 elements. So nothing else is said by this gap ID identification of the different groups. Very good. We have that, and we can just repeat exactly the same exercise, looking at the permutations that I can have in this particular scenario of the T2 over Z3 orbifold. I can inspect and find the selection rules that are also possible here, the possibility for the strings that are located at the singularities to interact, etc. And what I obtain is actually this group that can be written as the product of D8 times D8 over Z2, or equivalently Q8 times Q8 over Z2. This particular symmetry is also labeled by gap as a group, the 49th group of order 32. Very nice. So give a name. Now, what else can you know just simply from this geometrical point of view? When you write these matrices or the matrices related to these particular groups that you have here, you can actually ask, for example, gap, if you wish, which are the representations that your fields are building. That the fields, I mean the fields related to these particular strings related to the singularities. And it will tell you which particular representations you have. So in particular, in the 2 over Z3 case, you will have that in the bulk, there are only singlets, but there is a non-trivial singlet as well in the T2 over Z3. But in the twisted states, there will be only triplets, 2 different kinds of triplets. That is interesting. And all doublets are actually not in the massless spectrum. These are the massless states. The massive states can build additional representations under this particular traditional flavor symmetry. In the case of T2 over Z2, you have only trivial singlets in the bulk, in the untwisted sectors, and in the twisted sectors or attached to the fixed points, all these four red strings are actually building a fourplet of this particular traditional flavor symmetry. So, what else? Well, we have all the possible traditional flavor symmetries described by these fellows, I said, Kobayashi, Niles, and Ratz particularly, but also Plurga and Rabi-Guarter back in 2006, where you have to put together the permutation symmetries and the strict selection rules symmetries that you obtain there by a multiplicative closure. Sorry for my sign, but I didn't find any admissible sign in order to write this. So I will write the multiplicative closure like this. Now, what you can do in order to use this information is, for example, to make a classification of all the possible traditional flavor symmetries that you find in heterotic orbitals. And for example, phenomenologically viable models, this classification has been done. Very nice. Some people have found that delta 54 in particular appears very frequently in these models. Apparently, the T2 over C3 orbifold appears somehow as a factor in many of the orbitals that we have, in many of the in many of the admissible heterotic orbitals, and therefore it would be a very nice scenario to explore. We did it in 2016, and we found interesting neutrino physics, but I will not deal with this now, because basically the scenario was incomplete. I will tell you more about why it is incomplete here. So this is only one kind of the available symmetries that we have here. In particular, Lauamas and Niles told us back 30 years ago that modular transformations can mix different twisted states. And since they mix states, that means not only the traditional flavor symmetries appear mixing states, but also some transformations that transform the moduli that are not moduli universal relate different states living at different singularities. So we have to use them as well. Somehow it seems that the traditional flavor symmetries and these modular symmetries cannot be completely independent because they mix the very same states. But let us see more. So could it be that these are the so-called modular flavor symmetries that people are talking about nowadays? And can we determine systematically all flavor symmetries that we can find in these scenarios, including, of course, the modular transformations? The answer to this is positive, of course, but let me tell you how you come to that. People, like 35 years ago, started talking about Narayan orbitals. So orbitals were invented 35 years ago, and immediately Narayan, Samadhi, Witten, and some other fellows started writing a possible formalism in order to deal with these kind of constructions in a very nice manner, in a very general manner. In particular, they remembered that people were talking about heterotic string theory, where right movers and left movers were actually independent, completely independent, different kinds of strings, etc. So they actually were using different right moving and left moving modes. And Narayan took that really seriously and said, well, I could actually take the two real coordinates of the right movers and the two real coordinates of the left mover and compactify them independently. Actually, in different orbitals, if I wish. I won't wish to do that. I will want to keep the geometric part as close as possible. So I will perform the same orbital on the right and left movers, but let us see what we can win with this particular formalism. So the Narayan proposal is to compactify in these 2+2 independent degrees of freedom, and let us do an orbifold and a right orbifold compactification as well. So just as before, let us now propose that Y is not a two-dimensional real vector, but a four-dimensional real vector, and that contains right and left movers as is depicted here in the top. So, and now let us just perform a rotation, just like the twist that we performed before, but now in this Narayan 2+2 dimensional space, this theta, where I perform on the left movers and on the right movers the very same rotation. But now, for the translations, I will actually have the winding for one part and the Kaluza line for the other part. So I will use these different numbers in here, and I will use 4 times 4 Vielbein in this particular case, and people, well, he in particular and many other people as well after him, classified many different Vielbein that are possible in order to obtain admissible orbifolds. Symmetric like this, or asymmetric as those where these thetas are actually different. So we have this Vielbein here, and with this Vielbein you can have the different matrix that you can have for your orbifold. In particular, you can write all the different lattices in which which you can use for your tori, and these lattices are of signature 2, 2, etc. So I will not enter in more details than that. But the important thing is that you can combine this theta and this lattice gamma together in order to generate now the so-called Narayan space group. That is just simply the same thing that we defined before for the other stuff, but in general for the geometric orbifolds, and here for the Narayan orbifold, where we have 4 times 4 matrices all over the place. So these translations, I repeat, contain the winding numbers and the Kaluza-Klein numbers. Now, what did you do? Well, the Narayan space group will define all about your orbifold. Of course, we saw it before. Once you define your rotation and you define your lattice given by this Vielbein, if you wish, once you define that, you are done. You know precisely which orbifold you are actually working with. So you have these particular elements of the Narayan space group, and now the question is whether I can transform this orbifold without altering it. So if I can just simply modify a couple of parameters and obtain exactly the same Narayan orbifold or not. That is a question that we will ask. That is, we're going to figure out what the symmetries of this particular orbifold defined by the Narayan space group are. And in order to do so, it's very convenient to do it in the language of groups. So you might actually ask which are the possible automorphisms of this Narayan space group. And this can be decomposed as Bauer, Nilist, and Vodafone detected a couple of years ago, 2 years ago. And this can be split in 2 different cases: the rotational automorphisms and the translational automorphisms. For the rotational automorphisms, let me say that you can have perhaps many different thetas here inside the Narayan space group and say, yeah, I take the different thetas here and I map the space group to itself. So it is an automorphism, but it is an inner automorphism, and we don't learn anything new. We learn only that we have an Narayan space group, and that's it. But what happens if you find some rotation that those don't belong to the thetas inside these elements of the Narayan space group? If you have that, then you have an outer automorphism, a symmetry of your Narayan orbifold, something new, something that is not included in the original stuff. So sigma, since it is a rotation, will affect your metric, will somehow map the different moduli that are contained in the metric that is here, the generalized metric of your Narayan orbifold. And therefore, you have here, just encoded in sigma, a modular symmetry. We are transforming the moduli, right? And you can have as well, on top of that, certain translations. The translations will be just simply translations that are not included in the space group, in the Narayan space group. Remember that these n's were integers, 4-dimensional integer vectors. So you can have some other translations that are not full 4-dimensional integer vectors, some fractional vectors if you wish, to have something new, to have some outer automorphism, something that is not included in the Narayan space group. When you take into account that, you do not affect the translations, do not affect the metric, you do not affect the metric, you do not affect the moduli, but you really relate different points in your space. Therefore, if you remember your orbifold with different fixed points, you can relate with certain translations, you can relate the fixed points of your orbifold, and therefore the states living there. So you have something like the traditional flavor symmetries that we had before. Let me just put a couple of examples for traditional flavor symmetries. So I was saying you have these translations for the outer automorphisms that belong to traditional flavor symmetries, but it turns out that also this particular rotation doesn't actually transform the moduli. Why? But this is a minus identity. Remember that we have 2 blocks, 2 times 2, and each block might be regarded as a, I don't know, SL2Z transformation, and the minus identity does not transform the modulus itself in SL2Z. Therefore, this minus identity 4 times 4 matrix does not transform the moduli. It is also universal moduli space, and therefore you could say, well, this is also part of the traditional flavor symmetries. Let us put it together. Let us figure out all the transformations that are translations, and include this rotation that is here, and see what is the possible symmetry that you obtain coming out from T2 over Z3. So you compute them, you obtain, for example, this TA translation that contains thirds as integers, as entries, sorry, in the particular translation that is given here. You put this translation, and this rotation together, and you obtain a given group of translations of outer automorphisms. You do exactly the same with the T2 over Z2, but it turns out that translations are equivalent also to this particular element, and that's the reason why I don't include it. One particular translation is given by this, and now the next question that you pose is what you can obtain using these elements. So, for example, with these two particular translations that are given here, you relate the different points in this orbifold in the T2 over Z3, you relate these points that are given here, and this is precisely a permutation. This has to belong to S3, right? So it has to belong to the traditional flavor symmetries. In the case of the T2 over Z2, this particular translation relates these 2 points, and this is also kind of the one of the S2s that we obtain in the traditional flavor symmetries using just geometrical arguments. So very nice. If we just simply continue, you look at the 4 different translations and all the elements that are here, what you obtain at the end of the day is that precisely as you just expect, you obtain from translations in this -1 element, you obtain the traditional flavor symmetries that we had before. Nice. What do you obtain on top of it? Well, on top of it, you obtain also the rotations, the modular symmetries, and the modular symmetries that you have depend on the orbifold that you are doing, but they have to belong to the rotations that you can perform on your torus, and your 4-dimensional torus corresponding to your Narayan orbifold compactification, and these are these elements. These elements are a little bit mysterious. Let me just explain. This belongs basically to the S and T transformations corresponding to the Kähler modulus T, and these correspond to the complex structure modulus, the S and T transformation of the U modulus. This is the mirror transformation, and this is something very nice and something new, a CP-like transformation that's appearing there. Let me tell you in which sense these are this. Well, the KS and KT do not need further explanation, but the mirror transformation relate the 2 different moduli like this, and also the different generators of the transformations for the Kähler modulus and the complex structure modulus like this. And the CP-like transformation that actually was observed also by Novichkov, Penedo, Petkov, and Zitov a couple of years ago, relate basically the moduli like this. So I have here a sigma star as well, and it relates the moduli like this, and this is kind of a sign that we might have something that looks like a CP transformation. It's not quite CP, but might actually play the role of a CP transformation at a given point. So that is what we have, and I was saying that depending on the orbifold that you take into consideration, you can have different subgroups, different groups that come from these elements that are here. So you might have, for example, the full SL2Z or only one part of SL2Z. Why one part? Well, I told you that for T2 over Z3, the complex structure has to be fixed by hand geometrically in order to make it compatible with the Z3 orbifold that I want to perform to this particular value. So if I do so, basically I cannot just transform it to whatever value I wish, right? So I cannot perform all the SL2Z transformations that I have available here. But I can perform in particular this transformation CS times CT, and it leaves the value of U completely invariant, and you can see that at least at this level, this looks as a C3 modular transformation that you can have, or you have to take into consideration on top of the other possible modular transformations that you have here. In the case of T2 over Z2, basically all the transformations that I have here, all the symmetries that appear in the top, are actually free to be used. I told you that you have a TU transformation, the mirror transformation available because you have TU free, and you can have SL2T, SL2ZT, SL2ZU as well, and the CP transformation appears as well in this particular scenario. So everything very nice or complicated, I don't know how to consider it, in the T2 over Z2 scenario. What else can we learn from string theory in these scenarios? So what you know is that in particular, you know what the groups are in your, you saw already what the groups are, what the modular groups are in these particular orbifolds, but you can also figure out what precisely the finite modular symmetries are acting on the four-dimensional matter fields if you just simply inspect in the context of the CFT, the conformal field theory, what the properties are, what the properties of the vertex operators are, etc. People have computed since the 90s different properties for the different matter fields that are just appearing in our compactifications, string compactifications. For example, the modular weights. They cannot be whatever you wish. In particular, if you perform a Z3 orbifold, you are going to have thirds as possible modular weights, fractions, of course, right? And if you perform a Z2 orbifold, you can have half integrals appearing here. So this is just given in this particular paper. Also, there are some other papers where they computed the Keller potential, where these modular weights also appeared. In this formalism that I was saying, you can compute the modular transformations just formally of the vertex operators associated to the untwisted strings. That is something you can do. You can use, for example, the expressions given in Lawa Massenile's paper 30 years ago. And but what they tell us as well in this particular paper is that the product of different twisted strings can result in an untwisted string, in a bulk string. So you know the transformations of the bulk strings, and you know how to relate bulk strings to twisted strings. Therefore, you learn somehow how the twisted strings transform as well under modular transformations. That is a very nice news that you can use. You can read up the modular transformations, and in particular, you can read up the possible relations of the different states living at different singularities encoded here in this unitary representation of the modular transformation that you want to perform at a given point. So you are going to have the modular weights, you are going to have the representations, then you can use just simply gap for your particular case, your orbifold, your favorite orbifold, and you can determine as well the finite modular group that is appearing here in this particular scenario for all the different gammas that are unbroken, as I told you, that are not related to this complex structure that is being fixed by hand in the orbifold. Very good. So now, let me just simply exemplify what I'm saying by inspecting what the finite modular groups are for T2 over Z3. In particular, you know that the gammas that are unbroken in this particular scenario are those related to the transformation SL2ZT transformation of the Keller modulus, of course, and we will have also a CP-like transformation, and we will have an additional transformation that actually, I will tell you more about it, is related to the twist of our orbifold. This actually could be considered to be an inner automorphism. I told you that all the theta's that appear in our space group are actually inner automorphisms. But if you consider this living in a 10-dimensional scheme, that is in a 6-dimensional torus, this particular rotation is not actually a symmetry of the full compactification, of the full 6-dimensional compactification, and that's the reason why I will include it here as an additional element. I told you before that it was kind of a Z3. It was a kind of a Z3, but all these different elements can have different representations acting on the fields. These are my representations, my rows, right? These unitary representations that will build a finite modular group. And the finite modular group that they built in this particular case for Ks and Kt is the T prime, the double cover of A4 with order 24, as you already know, of course. And for the Cs sigma star, the CP transformation, this will transform the fields in this form. It will relate one field to its conjugate, so really like a CP-like transformation, very nice. And finally, we have this particular rotation. I told you that it is kind of the C3 twist. It is like the modular representation of the rotation that I perform in the orbifold, right? That I model out actually for my orbifold. So basically, I have this particular element acting on the modulus, and it looks, since these states are actually invariant under the twist, so this looks really like a diagonal transformation, but we must not forget that we have the automorphy factor. And this automorphy factor, once you fix u, remember that u is fixed to e to the 2 pi I over 3, you obtain really a non-trivial contribution here that looks like a C3 phase. So this was a C3 transformation, this is a C3 transformation, so at the end of the day, you get something diagonal that is a Z9 transformation. This Z9 transformation is related to rotations in the compact space. That is, it comes from the Lorentz group in 10 dimensions, in the original Lorentz group in 10 dimensions, and therefore it's a remnant of the Lorentz group. All the symmetries, the discrete symmetries that are remnants of from the Lorentz group in extra dimensions are built. It's known built R charges. Therefore, you can just simply inspect using this kind of formalism what are the possible charges for the different fields, given in particular a particular modular weight that you obtain. So let me just put the list of the different fields that you can obtain in this scenario, T2 over C3 orbifold. You have certain states in the bulk that have modular weights 0 or -1, and you can have in the twisted states living at the fixed points only these particular values for the modular weights. Very nice. Associated to these particular modular weights, I told you they appear here somehow. You obtain the R charges. The R charges can be 0, 3, 1, or -2, depending on the modular weights, of course. And also you can, as I told you already, you can also know from the shape of these particular representations, what are the representations that they built under the particular symmetry that you obtain here, the finite modular group T prime in this particular case of the T2 over C3 scenario. Very good. That is something that we wrote down last year in this particular paper. Also, what you can know is that, well, you know that your finite modular group is T prime, and therefore you know as well that your Yukawa couplings have to build modular forms. That is something that you can actually compute using, for example, this paper of 30 years ago or so, or that you can just simply trust because basically you are starting with a theory that is conformal, that is modular invariant, that has a lot of modular symmetries. So you can either do the actual computation and show that you have modular forms, or you can just simply trust that if you find this particular symmetry, your couplings, as Ferrulio described a couple of years ago, they have to be modular forms as well. Up to, of course, modular invariant function. This is not a form, but whatever, the J invariant function, right? So let me call these couplings just simply Y, as it's customary, and say that since you have T prime, now you can have the lowest modular weight possible, that is 1, and from there you can build all possible higher modular weights, just making tensor products of these modular forms. So these modular forms build in particular a doublet of T prime, a 2 prime prime of T prime, and from that you can just simply start building, I don't know, the other representations, the singlets, the triplet, if you wish, that you can find here, and also the other doublet that you can find in this particular case. Very good. That's what we have. Of course, since this is a modular form, it has to transform in this way. Since it has modular weight 1, then I can write here the 1 that comes with the automorphic factor. And of course, the representation under T prime of the particular element gamma under which I am transforming my modular form. Very good. That is what I have in the scenario. Now, T2 versus Z2, well, it is more complicated. I told you have two symmetries to start with, SL2ZT, SL2ZU. Well, you have too much. Everything that is different to the other case, to the previous case, is in blue in this particular case. So you have more elements that is depicted here, and you have, of course, more representations. You put all these representations together. You ask Mr. Gap whether you have a very nice group, and he tells you that yes, you have the group with order 144 and with label 115. Very good, but you can further inspect and you can see that this group is actually the semi-direct product of S3 times Z4 that is given here. So that is what you have. This Z4M is related to the mirror symmetry, but acting on matter fields. On matter fields, it is not a Z2, but a Z4. That is what we obtain in this particular case. For a ZPL-like transformation, you have just simply sigma star, as you know. Then you have a Z2 as the one that Bethe and his collaborators found out a couple of years ago. And you can have also this remnant, discrete remnant of the Lorentz symmetry that will, of course, yield as well an R charge. But in this case, since we start with this element and not the previous one, we have a Z4 R charge. So if you put together all these particular contributions in here, you can have the list of the different modular weights, the list of the representations under the finite modular group that is given above, and you can have also the R charges. With all these ingredients, of course, you can already start writing an action if you wished. But that is not all. Something else that we would like to learn is that what is this 144, 115 related to, I don't know, the finite modular groups that people are talking about all over the place? Well, Guillaume told us yesterday that there was something called symplectic groups, right? These symplectic groups, SP, 4Z, somehow with a different genus, with a different level, that somehow told us something about some additional modular transformations. What is what it's telling us here? Well, in the particular case of T2 over Z2, we have two moduli. These two moduli that are here. If you simply inspect the tables that Dean Leo Ferrulio told us yesterday about, you can find that there is one particular case where these two guys are actually free. The complex structure and the Kähler modulus are free. They are called tau 1 and tau 2 in their scenarios. And the actual symmetry that they obtain for this case is an order 720 symmetry, but if they restrict it to the case where only these two guys are free and there is one particular threat modulus fixed to 0, this particular symmetry of order 722 reduce to this order 72 order group acting on the modular. That is precisely what we have, precisely what we obtain. So basically what we find out is that this particular group that we obtain here as the action on the fields comes precisely from the general symplectic description that Dean Ferrulio and Leo gave us last year. Very good. So what happens if now we put an additional Wilson line? If we put an additional Wilson line, then we will have, in their case, it was just a third modulus, but in our case, in string theory, it's called Wilson line, as we found out last year. We will have precisely the scenario, the gamma 2 that Dean Ferrulio and Leo obtained in that particular case in their appendix E, in case you want to look it up. So you have a Siegel modular groups, and therefore all the couplings have to transform under the corresponding group, under the corresponding Siegel group. So you will have certain modular forms that are the Siegel modular forms here with parallel weight, that is for SL2ZT, SL2ZU, for both of them, you will have exactly the same weight in Y. And since you have S3 in the previous transparency, I put it, you have S3 appearing here, the modular weights will be just even. Yeah, this appears as a function of PSL2C over the congruent subgroup, of course, you know. Therefore, you can have even modular weights here, and then you just simply explore what is the shape of the Ziegler modular forms that are well known, of course, by mathematicians and physicists as well. You just simply write them down as modular forms, and then you see their transformations, and you figure out that basically they build this particular representation under the modular group that we obtain for our fields. Of course, the transformation that we have here, now that we have this parallel way, that we have Ziegler modular forms, is a little bit more complicated. It contains a part that depends on the modulus T and a part that depends on the modulus U. This is U. This is the transformation that we have here, ignoring, of course, the possibility of having the Zipf-like transformation also acting somewhere here, but I don't care about it at this very moment. So I have here, and now I come to the point where I have to somehow rest a little bit, relax, and put everything together. What do we have? We have certain traditional generators coming from the translational automorphisms of our symmetries of the Narayan space group, or for our default. And we have a modular, finite modular group as well, coming as well from the rotational now automorphisms of the Narayan space group of our default. Very good. We have these transformations. The modular transformations transform simultaneously the states living at the different singularities, and also the moduli living or describing the shape and size of my orbifold. And the traditional flavor symmetries, the translational automorphisms, they do not relate the moduli, they only relate the different states living at different singularities, different fixed points. Now, these two are not completely unrelated. In particular, the finite modular group turns out to be a subgroup of the outer automorphisms of the traditional modular group. That's nice. Also, on top of that, it turns out that the traditional flavor symmetry and the finite modular symmetry do not intersect only in the identity element. They intersect very frequently in the minus identity element, and it can happen that they can also intersect in some other elements. So if it is like that, it means that this union that is written here cannot be just exchanged by a cross or a semi-direct product. You have to do a mixture. You have to perform the multiplicative closure in here. Very good. What is what you obtain in one particular case? Let us take again our example, the T2 over C3 example, and build our eclectic scenario that is called this non-trivial combination of traditional and modular symmetries is the so-called eclectic scenario. So you know, you have the T prime, you have also the delta 54 traditional symmetry. Now, remember that the discrete remnant of the Lorentz transformation builds a Z9R symmetry. So since this is actually independent on the T modulus, and the modulus that is actually alive, that is free to do whatever it likes, it can be considered as part of the traditional flavor symmetries. So you combine these two together and you get to the point of a particular traditional flavor symmetry with 162 elements. Of course, I know maybe you're thinking it's a huge order already. Well, hold on a little bit because it can get worse. So now you combine together T prime and delta prime 54,2,1, and you obtain very nice eclectic group with 1,944 elements. A huge group, of course. This is the actual eclectic symmetry of this particular scenario without including CP. If you include CP, you just have to multiply by Z2, the Z2 ZP that we had there, and then we will have a group of 3,888 elements. That is what you will have at the end of the day. It's not classified by gap, then I cannot write very nice labels from gap, but you know already the order that you have here. Well, this is basically the scenario that we want to use, and I would like to explore in the next hour, in the next half hour or something, I would like to explore how to apply this first, and whether it can be generalized, and then I will like to jump to these other nice scenarios where you can use magnetized tori. So let me stop here and make a pause if you wish. Unless you have questions, of course.
Are there any questions?
I have a question. Hi, Saul. I'm Ferruccio. Nice to meet you.
Hi, Ferruccio. Nice to meet you too.
Now, concerning this distinction between traditional and modular symmetry arising from this construction. So I understand before you talk about this Narayan space group that in some way unify the two, you presented the two symmetries as having two different sources, modular coming in a sense geometrically from the redundancy in which you can parameterize the torus. And in this sense, I understand that this modular symmetry can be understood as a gauge symmetry, let's say. Whereas talking about the traditional symmetry, you were quoting selection rules. So I do not understand well if these selection rules have really the same status as gauge symmetry. I also tell you my concern or my, if you wish, what I have in mind. No, there is a difference between this modular symmetry and the traditional symmetry, because if I understand correctly, modular symmetry are always broken, which is good from the phenomenological point of view. Instead, these traditional symmetry, if I have understood correctly, are unbroken. So I would like to understand if really these traditional symmetries are really fundamental gauge symmetries of the construction, and if there is any mechanism by which they can be broken, let's say.
Yeah, let me just start by saying that, first of all, I was talking about string selection rules kind of historically, because it gives us a very geometrical picture of what these traditional flavor symmetries are. But in this scenario that I am just putting here on the screen, basically they have a common origin. You can just simply describe them, describe the traditional and the modular flavor symmetries coming from exactly the same origin, just as outer automorphisms of the Narayan space group of your orbifold, of your favorite orbifold. So in that sense, I could say they are kind of in the same footing. What is very interesting to me is that these particular translational symmetries that you have here on the right are related to those geometrical string selection rules that somehow seem to be kind of artifacts, or that were just simply elaborated by inspecting very carefully the conformal field theory and the symmetries of the conformal field theory, not at the level of your compactification in the space-time. So I think that somehow by looking at this comparison, the geometrical comparison, and this common origin, you can say that if you can just realize one of these symmetries as a gauge symmetry, the other should be also a gauge symmetry in your theory. That's what I could say.
I see.
And can it be? Maybe?
Sorry.
We explicitly have shown that the traditional symmetry has a gauge origin. If you go in string theory to special points in moduli space, you get enhanced gauge symmetries.
That's true.
And we have seen, at least for a few of the generators of the traditional flavor symmetry, that they are unbroken remnants of these enhanced gauge symmetries. So
absolutely,
they are
you're right.
Exact gauge symmetries of the string theory.
I see.
And if you break them, you need a flavon. So if you want,
yeah, that is something that I didn't answer. That's true.
You need a flavon.
Yeah.
Yeah, and yeah.
Sorry.
Mm-hmm. No, come on.
Can it be that these traditional flavor symmetry arising in this type of construction disappear if you go, let's say, beyond the orbifold construction? If you how to say, remove the singularities that are attached to the orbital construction. Can it be? Or
yes, I think so. For example, Stefan is here, Patrick is here, Hans-Peter is here. They all have actually made the blow up of different singularities of different orbitals. And what happens basically is that there are certain modes, certain twisted modes that develop VEVs. I mean, the scenario blowing up a particular orbital is equivalent to simply to giving VEVs to different particular fields that are living at the singularities at the fixed points. And therefore, in a phenomenological point of view, is actually like giving VEVs to a flavon, right?
Okay.
So yes, the answer is yes. Phenomenologically, you would say I'm just giving VEV to a flavon, but from the geometrical point of view, you would say I'm blowing up the orbital, for example.
I see. I see. And if I may, I have a last curiosity about when you instead talk about the Narayana space group and you show how these traditional flavor symmetry arise. If I have understood correctly, you said that modular came from rotation and traditional come from translation.
Mm-hmm.
And here I am a little bit confused because, for instance, in this T2 over Z3, in the last table you show, for instance, if I can see this table.
Yeah, I just go there. Sorry, it's a.
Yeah.
Mm-hmm.
For instance, the traditional flavor group at a certain stage is this delta 27, which is a non-abelian group. However, translation are abelian transformation. So I do not understand well how a non-abelian traditional flavor group can arise from just translation.
Yes, let me just go to this, I guess, it's a beautiful picture. And I think the simplest scenario is this one, for example, that I have on the right, this one that's here. And I have translations in the Narayan space group. This corresponds to a translation along this direction. And if I put a 1/2 in this particular case, in the second entry, I could talk about a translation in this direction. What will happen? Well, if I just perform the T1 transformation, the translation that is here, basically the 2 points that are here, are related to the 2 points that are here. And since we are actually talking about states, basically the states living on the left will be mapped to the states living on the right. And if I perform the second translation, then I will map the states living down here to the states living up there. And then I have a second set of transformations, right? And now these two transformations that I just described, and I just described 2 of the 4 possible translations that are here, build already a non-abelian flavor group because it relates these different states. Let's say that I put there's the level 0, there's the 1, there's the 2, and there's the 3, or well, whatever. You can write the different matrices for the different representations. 0, 3 is mapped to 1, 2. Therefore, I don't know, let me just try it. The 0 goes to 1, then I have something like this. And the 3 is mapped, damn it. The 3 is mapped to 2. Then I will have something like 1 here.
This is a 1. Commuting.
Yes, well, yeah.
What you need to do is the other translations, which are acting non-geometrically. And then it's really, I think it's a matter of the quantization of the string. That the translations, even though you first have an intuitive way that they commute, I think it must be related to the quantization of the string that at the end it does not commute. And it's really related that you do the translations now in this non-geometric fashion in the 3rd and 4th direction of your vector. Sorry for interrupting.
No, it's fine, it's fine. But what you say is that these 2, well, it was not clear to me that these 2 actually will yield a Z3 times Z3 or Z2 times Z2, you mean?
I just checked in the paper, yes.
Damn it.
So this
does
not help. You need the other translations and then they don't commute. And the other translations, they are kind of non-geometrically because of this Narayan language.
There is another space. In which I can realize this transformation, and in this other space, these do not commute.
Yes, there's in a way there's a T-dual space with dual coordinates, and these coordinates don't commute. The actual coordinates and these dual coordinates, these actions don't commute. So it's very much related to this generalized geometry, which is also highly studied in the theory literature. So there's this double field theory, generalized geometry discussions, and it's somehow related to this.
Okay, thank you.
Thank you.
Could I just make a short statement about the discussion? If you take the theory from the point of view of conformal field theory, in principle, you would not even see a difference between these various symmetries. Some of them are realized, some of them might not be realized. Of course, on orbifolds, if you have this strict symmetries, more of the traditional flavor symmetries are realized. And so from the point of view of that, you have left movers and right movers. And if you start doing things, mixing them, then of course you will get into this question of the modular flavor symmetry. But I guess in a certain way, the symmetries are inherent in the fact that in the string you double, in principle, the degrees of freedom. You on the worksheet, yes. Right movers and left movers, yeah. And when you do something to the right move, you can sometimes do something to the right movers which you do not do to the left mover, as doing these shifts. And if you iterate that, and you can get all these actually non-trivial symmetries, which are not abelian, although the special building blocks might look as if they were. I think that's in essentially the picture. You have to be very careful when you interpret these things strictly geometrical, because they are not strictly geometrical symmetries if you're dealing with left and right movers.
But I mean, just one comment. I mean, the defected translations commute is only true strictly in Euclidean space, and this is not what's happening here. On the orbifold already, if you have the so-called shift, that sometimes a little bit leads to confusion because it's really a shift in sort of phases. And these things are generalizations, and there's no reason for them to commute. Yeah, so that's if you have a Euclidean space, okay, then it's commuting. But if you, for instance, just sit on a sphere, then these translations may not commute anymore. So I think there's no really contradiction between this statement that this form non-abelian groups, and these are translations in at some level.
Thanks.
Yeah, that would be great.
Recording in progress. Very good. So let me just continue here. You can also, let me just summarize. You can just make the list of all the different modular weights. I told you already that we have 0, -1, -2/3, -5/3, that you had these representations under T prime, that you had these representations under delta 54. By using these ingredients that are just given above, now the thing is, what do you win? What do you win from string theory by giving you all these different ingredients? So basically what I want to tell you is something about the good things that you can obtain, the power of these eclectic flavor symmetries that you obtain from these compactifications. So in particular, one thing that I consider very powerful is how it restricts the Kähler potential. So basically, let me just focus on a particular field with modular weight -2/3. There's one, oops, sorry. This -2/3 that is given here with the representations that are given here on the under delta 54 and T prime. And then just simply let's use the general form of the Kähler potential that can appear, as it was also written in this particular paper. I will tell you more about this. So this is the general form. So you have a series of contractions, including the modular forms that you have in your construction coming from T prime. They transform under T prime as a 2 prime prime, as I already told you. And these guys, these phi n, are just simply these triplets that are just given here. Let me denote them, the triplets, with these entries x, y, and z under delta 54. But let me just stress that we do not have a 3, 3 under delta 54 and a 3 under T prime, but we have only one triplet, and it decomposes differently with respect to T prime and differently with respect to delta 54. Actually, with respect to T prime, the same triplet looks like a 2 prime plus 1 of T prime and builds this particular representations that are given here. So in terms of x, y, and z, that are the entries of the triplet of delta 54. So I know that this part is particularly confusing, but the thing is that you have just simply to write everything that is just compatible with these transformations, with these representations, and see whether it tells you something about the structure of the Kähler potential in this particular case. What we find is that if we impose only T prime, basically the Kähler potential looks very complicated, right? You have the diagonal, the canonical terms with certain coefficients A1, A2, A3 that I don't care about right now, but you have also non-diagonal, non-canonical terms appearing here. So that's bad, of course. But now, if you just inspect what the traditional flavor symmetry gives you, it gives you further restrictions to kick out all the non-canonical, all the non-diagonal terms of the canonical, of the Kähler potential. So you are left only with this particular combination of the components of your triplet of delta 54. And that is kind of natural, right? Because in delta 54, the only thing that you have in the Kähler potential is the triplet and the anti-triplet together, multiplied together. So it has to give you a singlet, a trivial singlet is here. So basically, this behavior is coming entirely from the traditional flavor symmetry. And we observed that this is not only the case in the scenario with delta 54 in the T2 over Z3 orbifold, but also in the T2 over Z2 orbifold. That will happen as well. So you will have that the traditional flavor symmetry, the traditional non-abelian flavor symmetry that will appear in G eclectic will fix the canonical Kähler potential for you. So that is very nice. And that is very nice because, of course, you remember that when you have all these terms, and this paper was pointed out that predictability is just kind of not so safe, right? So right now, with this kind of combination, you have something nice. On top of that, you can also remember that you have a huge group, right? 1,944 elements of your eclectic symmetry is what you have before you break, of course, the modular symmetry, before you give vebs to flavons, before you blow up, etc. You have all those elements. So basically using those elements in the vacuum of your theory before you use anything else, you compute the superpotential and you obtain this nice structure that is here. So basically the structure that is here tells you that if, for example, X1 is a quark doublet, X2 is an up quark singlet, and X3 is a flavon, and C1 contains the VEF of the Higgs, basically you have a non-trivial structure for your CKM matrix, if you wish. Of course, you have to include as well the QD prime phi term in order to obtain also the other part of your CKM matrix, of course. But the point is that with this particular structure, you can start thinking about the possibility to realize nice phenomenology. At this moment, we don't see it directly, and we haven't performed the complete analysis in order to know whether or not this will yield a nice phenomenology. But you have this particular freedom of this particular flavon. I don't know, the subindex 3 will be for a triplet of flavons, if you wish. But you have also the possibility of giving VEFs to this guy, right? To this guy, to the killer modulus. And when you give that, you will break the modular symmetry. Of course, you will reduce your 1944 elements to a subset, a subgroup of this. And when you give that to the flavon, you will reduce also the traditional flavor symmetry. And something that preliminary results somebody just inspected is that basically you could break completely in the vacuum when you have settled the VEPs. You can break completely the flavor symmetry. Whether or not this is phenomenologically okay or not, this is a second question. But at least you can break completely the 1,944 elements that you can have here. That is one thing. Well, and let me just walk on and go to a very nice scenario that was concocted like 2 years ago, the so-called local flavor unification scenario, where you have to remember that if you have a very nice stabilization mechanism, you can actually set the VEPs of your moduli, say that you have T2 over C2, to certain values. And that these values can actually land on so-called self-dual points or fixed points of your moduli space. For example, complex structure equal I or complex structure equal e to the pi I over 3. They are very nice self-dual points where actually what happens is that the modular symmetry that in general in the whole space is not realized linearly, at those particular points, it happens to be realized linearly. If it is realized linearly, if a part of the modular symmetry at least is realized linearly at those points, it is worthwhile to take a look because those particular symmetries will behave as traditional flavor symmetries as well. And therefore, they will enhance your traditional flavor symmetry again. This will give you this particular scenario of local flavor unification where picking up parts of traditional flavor symmetry, of R symmetries, and of modular symmetry, you end up with a larger traditional flavor symmetry, enhanced traditional flavor symmetry, so-called unified flavor symmetry here. So this is the thing. So the thing is you have to combine the elements that leave this particular fixed point invariant from your modular group and put them in the so-called stabilizer. That is something that Guillaume taught us as well yesterday. If you just put these elements combined together with the traditional symmetry and with the R symmetry as well, what you end up with is a unified flavor symmetry, a local flavor unification scenario. Local in the sense that you have to go to that particular location. It could be a loci or a fixed point in the moduli space. What happens is that, well, you perform a modular transformation that is just in the stabilizer, and what happens is that it will give you one phase. This is not any longer something that depends on the modulus because the modulus is fixed at this particular fixed point or locus, and with a given modular weight together with a unitary representation of your transformation acting on the field. So it looks basically at the end of the day as a unitary representation, just a matrix, linear matrix acting on the field. There is universal modular space. It doesn't depend on the modulus anymore because this is at the end of the day just simply a number in at the fixed point. Very good. That is what you have to enhance your symmetry. And what happens as well? Well, it happens as well something that Bethe and Novichkov and collaborators pointed out, as well you, Ferruccio, pointed out. Basically, you have a scenario of a VEF alignment, if you wish, related to the fact that the Yukawa couplings do not transform anymore. So since they do not transform anymore, you have basically an eigenvalue equation that will set somehow the duration up to one parameter or so, one parameter of your VEF direction, where you have the modulus, basically. So you have these particular multiplet of Yukawa couplings that depend on the modulus, and just by solving this particular scenario where you are living at a fixed point in moduli space, you fix the direction of values of the Yukawa couplings. Very nice. So this is kind of a flavor alignment mechanism, but in moduli space, of course, as you all know. What are the symmetries that you can find here? What are the local flavor unification scenarios that you can have here? So you have to remember that we have to inspect different points and different loci. So we have the green curve, the blue curve, the orange curve, and the points black and blue that are given there, where you find different modular transformations that are left invariant. And these modular transformations that are left invariant leave the value of the Kähler modulus invariant, of course, and they are realized at the level of transformations on the fields as linear transformations that enhance your flavor symmetry. So this enhancement, without including the star that is given here, without including the CP-like transformation, the enhancements can be just simply these groups that are given on the left. So the largest group that you can have has order 324 elements, has this order labeled 111. 486, sorry, 486. This is the largest enhancement that you can have, and the largest enhancement that you can have is precisely at this particular point. This happens as well when you include the CP element, I mean K***. If you include that, you just simply kind of multiply times 2 the order of the group that you had before. This is the enhancement that you can have. You have still a lot of elements to go. You can do the same in T2 over Z2, and you find even larger groups. For example, this one that is here is it has 2,304 elements. That is the multiplicative closure of these two symmetries has order 2,304 elements. So that is what you find at this particular element for the case related to the tetrahedron. This is the nice guy that we decided to call the tetrahedron, and this is our nice raviolo, right? In the particular case of the tetrahedron, we have at this point this huge enhancement of the traditional flavor symmetry. In all other cases, we have also enhancements, but they are not as large as this particular one. Let me just point out that here we have the boundary of the fundamental domain of this particular T2 over C2 orbifold, this curve called lambda t. This will play an important role in the next plot. In this particular plot, I'm just depicting all the different enhancements of the traditional flavor symmetry that you can have, just putting as x's this lambda t, and also the analogous for the U SL2CU plane for the complex structure plane. And I can see that there are huge groups appearing all over the place. These are all possible local flavor unification schemes that you can start with. If you want just simply to inspect phenomenology, you can start with one of these symmetries, and then at this particular point, assuming that someone stabilized the modulus at this particular point, and as Bethe did, perhaps perform a little bit of perturbation theory to go a little bit away from this particular point or whatever, something different, right? So that is something that you can do, but you have to start from these particular symmetries. Now, let me just come in a very short summary to something that people have inspected in the last few years, last 15 years or so. Compactifications on torus with fluxes, with the magnetic fluxes. This is the so-called magnetized toroid compactification. There was a very nice paper in 2004 by these fellows, Cremades, Ibanez, and Marchesano, who computed just by using, I guess there was something before, but let me just tell this paper, compute the amplitude of the Yukawa couplings as intersections of different wave functions in the compact space. So that is what they did. And the compact space is just simply a torus that has some fluxes, some magnetic fluxes coming from a U1 or from a UN theory, if you wish. So that is what they did. And just by doing this computation, they actually figured out the global structure of the Yukawa couplings to start with. And they figured out as well that you could actually perform on this some modular transformations and see what happens. And this has been exploded during the last 2 or 3 years, more strongly by the group in Japan and also by a subgroup in Korea, by these fellows that are here. And recently, the students Al-Mumin and Shukla, together with Mochun Michael, Victor as well as another student, and myself tried to figure out whether everything was done kind of according to what we thought was correct. And what we figured out is that there might be some other questions somewhere. But let me tell you something about what we're going to obtain. What we're going to obtain at the end of the day out of these scenarios is that you have to go beyond the scenarios that I have presented so far. I have presented cases with several moduli. I have presented cases with double cover of gamma n groups. But what I haven't presented so far is the existence of fractional modular weights for the modular forms. For the states, it is possible, there is no discussion. For the strings, it is possible, it's always there, you have fractional weights. But in our cases, in the orbital cases, the modular weights for the modular forms were integer. In this particular case, it happens that it will not be like that. And that's the reason why I will jump just short, very short, to tell you something that also Guillaume told us yesterday, something about metaplectic modular groups. So basically, when you have integral modular weights for modular forms, you have to consider a larger group, the double cover of SL2Z, the so-called metaplectic 2Z group that we just simply abbreviate as gamma tilde. This gamma tilde contains elements that are just very similar to the SL2Z, but since modular weights, not modular weights, yes, since modular weights now are half integral, the associated automorphic factors in the transformations will not be quite well defined, right? Because you have this square roots, the square root appearing all over the place. Therefore, you will have to add something in addition, the so-called multiplier, or if you want, the co-cycle factor. This has many possible names and many possible origins. So I will just simply say, well, this guy, you have to add this epsilon that can be either plus or minus, and you have to start with a convention. How you start. Of course, Liu, Yao, Ku, and Ding set a very nice convention, just computed directly what these multipliers are, but some other fellows, in particular the Kobayashi group et al., use a completely different convention, so you have to set it somehow. And that is what we do. We use, for example, a generator of this metaplectic group S tilde that is just given by S from SL2Z and -1 as the multiplier. And for T prime, we use T from SL2Z and +1 as the multiplier. Just by using this, you can see that you respect the defining relations of MP2Z, the metaplectic group, that are these ones. So these are the defining relations that are very analogous to the relations of SL2Z, but notice that you have a huge power here. Instead of 4, you have 8. That is the largest difference in this scenario, of course. Now, in this particular case, the modular forms that you can have, the metaplectic forms, let me call them like that, transform like this, with this square root, and you will keep always the positive root in this case, but there is kind of an ambiguity that can be just simply get rid of using the conventions by Liu, Yao, Ku, and Ding on this particular guy, is the multiplier. Once you put all the ingredients together, you have this automorphic factor or modified automorphic factor. You have a unitary representation, again symmetric, acting on this particular metaplectic modular form that I have here. That is something that we want to have, that we will at the end find in our scenarios. So what we want at the end of the day? Well, as before, we want to have a finite modular group, right? A finite metaplectic group. That is what we want to have. And it will come out as usual from the quotient of the global infinite group and one of its congruent subgroups in order to obtain, in particular, this finite group. So this finite group, of course, is defined as this or like this. In particular, this relation is crucial, as you all know, from the definition of gamma n and gamma prime n. So it's just the same, but in this case with the tildes all over the place. But it turns out that for n equals 1, you do not have any extra relations, but for all n's larger than 1, you have to add, like in the case of the gamma n groups as well, you have to add certain additional relations in order to obtain the finiteness of this group. Basically, this group is finite, but in order to write it very nicely in a presentation, you have to add certain finiteness relations. The groups that you obtain are very large. Immediately here, you have the double cover of gamma prime 4. Gamma prime 4 had order 48, and here you have gamma tilde 4, then it has double. right? And gamma 8 prime, it has really a huge order as well. And that's the reason why you obtain immediately 768 elements, immediately with n equals 2. And with n equals 3, you obtain a huge order. Huge orders are all over the place in metaplectic groups. Nice. Or not nice, I don't know. That is what you have. So what is this compactification and magnetized tori? So basically what you already have in mind is that if you want to obtain modular symmetries, somehow the tori have to appear somewhere. And that is what they do. They compactify on a torus, first of all, as before. So you have the torus, and you have, instead of y, we call the complexified coordinate in this plane, z, and the boundary conditions for everybody living here in the torus have to be such that respect these particular conditions of the orbital, right? So you have to identify the top with the bottom and the right with the left, and that is what these conditions, the geometric conditions, tell us in the complex space that describes our torus that is given here. So these transformations just transform the coordinates z like this and the modulus like this. Just we know that. Now what we do is to add, in this particular example that I will put, a U1 magnetic flux. That's what I do. I add just simply a particular vector field that will generate a flux along the directions of these terms. That's what I do. And I will demand that is quantized. That is what I do. They demand that is quantized, that is this particular integral, and the torus gives you an integer, an arbitrary integer in principle. And if you do so, to expect just the transformation, this is a U1 transformation, of course, this transformation that is here on the vector. If you do so, what you obtain for the transformation of matter fields will be, of course, a U1 transformation, right? Something that you have to demand as part of your boundary conditions. So let me tell you more. What you want to know right now, what Grammatis et al. Wanted to know, is what the wave functions that describe the behavior of our matter field in the compact space contained describe, what they look like. So that is what they wanted to find, first of all. And they said, well, let us focus on spinorial wave functions. They have to fulfill under the conditions of being in the torus and the conditions of being affected by a flux, a magnetic flux, U1 magnetic flux, if you wish. They have to respect the Dirac equation. So they solved basically the Dirac equation, and they focused on the zero modes of this Dirac equation. This gave you waves, of course, wave functions. So now they have this. These are the classical wave functions that you have there. And now let us just impose the additional boundary conditions where you have a U1 transformation at the different boundaries, right? At the boundaries that are related by different points by the transformation that made your torus true. So these transformations that are here, these relations that are given there, have to relate, have to be seen as boundary conditions for our solutions that I have here. Now, let us put separate these spinors in the compact two-dimensional space, if you wish. Let us split them into parts, the plus and minus part, and let us focus just in those plus parts that are related to positive fluxes. So I don't care about the negative fluxes because there will be a relation between them. So I don't care. Now, they wrote down the actual expression for the solutions of this equation, for these conditions, for these zero modes, and they found this expression that contains a Jacobi theta function. That is the interesting part. So you have something that depends on the Jacobi theta function, and you know, that have been working with modular forms all over the year, you know that these Jacobi theta functions are crucial for modular forms. So there is something modular going on in here. So very good. Now they counted as well the number of zero modes, and they said, well, there are M of different modes. So M different flavors, M different states that have otherwise exactly the same quantum numbers, right? So if M is equals 3, then you will have 3 quadruplets or something like that, right? So N is just simply a number that depends on the volume of the compact space, etc. We don't care too much about it right now. So, but this tells me that psi, this wave function, has a modular behavior. This is something that we know. And then we are wondering whether we can compute just simply transformations, and we just do it by hand. You just simply go on, transform Z, transform tau, and see what you obtain. And what you obtain is something similar to this. There is a subtlety here and the ambiguity of the definition of the Z coordinate, and a phase that I didn't write that is not very relevant, in particular for the T transformation. But basically, the transformation has this shape. Having this shape tells you that your modular weight is 1/2 for this particular wave function. Look, this is not a 4-dimensional field, right? This is only the behavior that's happening in the compact 2-dimensional space associated to the torus with the fluxes. Now, what you have to go on and inspect is, well, put together all these rows and see what happens, right? To see just simply what was going on with this particular choice of rows that are the result of just simply computing the transformation properties of the different M0 modes of the size, and you obtain these matrices that are given here. Very nice. So you don't know what I mean, but in principle, you could actually go running to Gap and ask, well, tell me what the group, the finite modular group is that is related to these particular representations, and it will tell you something perhaps. But the point is that these are the wave functions. These are not our fields, and they are not our modular forms representing the Yucca couplings. Then you have to go on. You go on, and you ask yourself, that is something that people have asked several times, you ask yourself whether these particular solutions with these particular transformations are compatible with the particular transformation properties with the boundary conditions that we imposed before. And people were finding that they are not, but it's because they ignored this subtlety about the ambiguity on the Z, on the definition of the Z coordinate, and that one particular phase that goes here basically can be completely ignored in the effective field theory because of the following slide that I will show. But let me just tell you that they satisfy the boundary conditions before and after transforming the modular these wave functions in the compact space. That is something that was proved in these two particular papers, so that you can take a look at that. And then the final point, and that I think that is very important, and that is what started Ramos et al. 15 years ago, is that you can compute, I was saying, the Yucca couplings. That is the amplitude of interaction between different states living in 4 dimensions just by inspecting the integrals over the torus, over your compactification of different fields, different wave functions that are associated to your 4-dimensional fields. This, of course, since it is located in the torus, will have a modular dependence on that particular torus that I showed you before with the fluxes. What with it is just simply to compute this particular integral once more in general, and notice that it will look again just simply as a Jacobi theta function. So if it is a Jacobi theta function, just plainly a Jacobi theta function, just using mathematics, very complicated mathematics from my point of view, algebra, you can show that this is just simply a Jacobi. Perhaps you can compute the transformation of these Yucca couplings. And if you do so, what do you obtain? What we obtain is that we have certain transformations with modular weight, again, 1/2, with certain matrix representations of the different elements, particularly of the generators S and T tilde. Yeah. And now, yes, we put them directly because these are our modular forms, right? This is Ferruglio's prescription. Your modular forms, your couplings have to be modular forms, and they have the symmetry, the flavor symmetry, the modular flavor symmetry of your theory. In this particular case, is basically a metaplectic gamma 2 lambda group. This is the final metaplectic group. There is the one that I presented before. And these guys, these Yucca couplings that are here, actually build multiplets of this gamma tilde 2 lambda. And lambda is related to the least common multiple of the number of flavors. You know, this number of zero moods that we had for the different wave functions that we have included here. We can have M1, M2, M3 if you wish. And let's come on multiple of this will give you lambda. So you can have different scenarios with different combinations of generations of quarks, leptons, Higgses, etc. And at the end of the day, arrive to a scenario where you have small or large group. And that is something that has been going on during a while, in particular in our paper. We presented a series of examples, and this particular paper is given here. The final thing that I want to present here is that you can also know what the transformation properties of your four-dimensional fields are. So you think about the six-dimensional field, omega, in this particular case, yeah. You think about it as the composable into the four-dimensional part and the two-dimensional wave function. So we know the modular weight of this guy. We don't know the modular weight of the four-dimensional field. We know that the six-dimensional field does not have to have any transformation on the modular transformations, because it is a six-dimensional thing that lives all over the place, right? So it doesn't have to transform under the modular transformations that I apply just simply to the wave function. So just by doing so, we can just simply say that these two guys have to have opposite modular weights. And that is what happens. The modular weight of the four-dimensional matter field is -1/2, the opposite of the wave function. And we have also certain matrices that you can just choose to be kind of the same matrix that was the inverse of the matrix that was transformed psi up to a phase, a convenient phase that we just envisage in order for these matrices to be compatible with the group of the modular forms that we already figured out. So this particular phase is kind of ad hoc in order to be compatible with that particular group. And what we find out is that, of course, these guys, these 5 fields, four-dimensional 5 fields, also build metaplectic representation of metaplectic groups. One observation that is very interesting to me, at least, is, and I guess to Michael as well, is that anywhere, we didn't mention supersymmetry in anything of this. We didn't use supersymmetry. Maybe it's hidden somewhere, but we didn't use it explicitly. And then it seems that all of this behavior that we are describing here with the metaplectic groups, etc., describes as well a non-supersymmetric picture of modular symmetries. Somehow supersymmetry is hidden because these metaplectic symmetries are holomorphic, of course. And therefore, one could like to figure out how to get the non-holomorphicity of a normal theory. Perhaps you don't get it, just simply because somehow it's related to a supersymmetric theory. It comes from string theory, and at a given point, at least in 10 dimensions, at least in the worldsheet, you have supersymmetry. Perhaps it's like that. Let me just now go and finish. I guess it's time. Where are we? And what is still missing in these scenarios with modular symmetries? Well, I presented to you a particular scenario with toroidal orbifolds and with toroidal fluxes, where we have really a huge number of elements in each modular symmetry. We have, first of all, 2 kinds of symmetries. We have traditional and modular symmetries. You have, as you saw and you said, Ferruccio, as well, you have a common origin for traditional, modular, and simple-alike symmetries. And we have also a combination of these symmetries that might be actually interesting, at least to fix the Keller potential. At least for that, it might be interesting. We have restrictions all over the place. The huge number of elements in these symmetries tells us that basically we have really a very constrained scenario. It might be over-constrained, we don't know, but this is a very constrained scenario. So if we find something, we can be almost sure that there is no other chance that this is something, even if it is positive or negative. If the answer is 1, probably we don't be able to do much to improve it or to discard it if it is a positive result, because of all the different constraints that we have: modular weights, representations, Keller potential, etc. Also, we have the possibility of having multiple moduli, depending on your choice of orbifolds, or you have modular fractional modular weights for your modular forms as well. So you can have either the traditional already traditional flavor modular forms, or you can have symplectic or metaplectic forms as well. Now, what is what we want to do next? Well, there are certain technical questions that we have to clarify as well for us, but I think we already are in position to address some questions of phenomenology. We can already start building the superpotential, building the matrices, the mass matrices, etc., coming to different points as you guys in the bottom-up approach do. We are already in this scenario where everything might be or nice or bad, we don't know. We have perhaps already the beginning of a complete non-supersymmetric picture, at least in the context of these toroidal compactifications with fluxes. So we have to take a look at this. We really don't know whether we are in the correct path or not, but that could be a very good idea to start with. And just to end, Wilson lines. So I mentioned just briefly that whenever we had the symplectic symmetries, we had, or you had, Roger, Dink, Liu, you had already a third modulus that is actually identified in our scenarios, in string scenarios with Wilson lines, and then we can kind of marry your work with our work and see that everything is just matching together. It appears that all what you are discovering there, it comes somehow from string theory. So include that and see whether we can learn more than what you already know could be a very interesting question. And of course, not only in those scenarios with orbitals, but also in toroidal compactifications with fluxes could be a very nice idea, something that we have and we are exploring already right now. Well, that could be it. Thank you very much.
Okay, let's thank the speaker.
Thank you.
And I think there's time for questions. Other questions?
My first question is whether you will arrive to your lecture, Michael.
I will, but you will probably talk longer than.
No, I want to go.
Soon I will pick up.
Maybe I could add a small comment about the non-SUSY picture.
Yes.
Also on the orbifolds, when we do our outer automorphisms of the Rhine space group, I don't see where we use supersymmetry there.
That's true.
So it's just, I don't know whether it's also somehow hidden, but at the moment I don't see where we use supersymmetry in order to derive our modular group, our finite modular group.
Yeah, indeed.
Just a comment.
Well, no, thank you.
Well, I have the impression that when you look at the superpotential, that in some way, in a non-supersymmetric theory, that in some way respects the superpotential of the parent supersymmetric theory. The deviations for flavor come from, let's say, the scalar partners or so. They, of course, have not been discussed here. You know? Usually in a supersymmetric theory, you put these scalar partners very heavy, and then the flavor symmetry in some way is not in a certain way disturbed by that, because that's the superpotential, and superpotential just is the very stuff which also survives in the non-supersymmetric case. I think that's the picture. That's the reason.
In some ways, this is, maybe let me comment, is already pointed out by Ramos et al. And probably many earlier works. There are two holomorphicities at play here. There's one of the superpotential, and then there's this other one where you use this index theorem in extra dimensions. And I don't think you can disregard SUSY totally, but what Ramos et al. Point out, in which we just quote, is that you can introduce very large SUSY breaking without disturbing the scheme too much, because in a certain way there's this.
Yeah, but that is also true in the orbifold case.
Yeah. It could be.
It's just, it's not this question of that you have a non-SUSY picture in the metaplectic case is not different from that you have also a SUSY interpretation in the orbifold case. I just as long as you consider the superpotential, you in a certain way take over all this holomorphicity which you have in the supersymmetric theory.
Sure. The question is why you would do that. And there's a reason, and I agree with you that it's also present.
No, for example, if you go to the Kähler potential, then you will have different. You will find the soft breakings of supersymmetry.
Oh yeah, absolutely. Yeah. But the question is whether you can play with these forms which depend on tau and not on tau bar, whether there's a justification for that. And there isn't. So that's the point. So I totally agree that there are major corrections once you blow this away. Yeah? But there's a question whether it's sufficient to look at these forms which depend on tau and not on tau bar. And there seems to be a reason. And this, you probably know, this has been pointed out in the old days, and we just recycle it. And that certainly doesn't depend on the metaplectic structure. So I have to go. Have fun. Hope to see you in person very soon.
Thank you, Michael.
Bye-bye.